Okay, we want to solve Harvard MIT 2021 Math Tournament Team Round. Problem number 6. Okay, if you had any question about the solution, feel free to send message to my WhatsApp number in the description and comments. Also, you can use my playlist on top of the video. There are lots of Harvard MIT Math Tournament and with many ideas that are useful for math. And you can improve your problem solving. Okay, so please subscribe my YouTube channel and turn on notification and like my video. So let's solve this problem. Let f of x equals x squared plus x plus 1 determine with proof all positive integers n such that f of k divides f of n whenever k is a positive divisor of n. So it means what? K is a positive divisor, positive k divides n whenever k divides n, then f of k divides f of n. Okay, so for solving this problem, we should check, for example, some small example. And for example, we can say always k1 is okay, satisfy this. So 1 always divides n. So f of 1 divides f of n for all n. And it will be what? N squared plus n plus 1. And f of 1 is what? 1 plus 1 plus 1, 3. So 3 divides n squared plus n plus 1. Now, if I consider with congruency, n mod 3 is 0, 1, or 2. And if I consider n squared plus n plus 1 mod 3, it should be 0. The first one will be 1, the next one 1, 1, 1, 0, the next one 4 plus 2, 6 plus 1, 7 will be 1. So it is bad. It is bad, so this one is only good because n squared plus n plus 1 is congruent to 0 mod 3. So here we found one necessary condition, that n mod 3 should be 1. Now, we should check some small examples. So let's check, for example, n1. n1 is okay because 3, 1 squared, the only divisor is 1. 1 squared plus 1 plus 1 divides 1 squared plus 1 plus 1. It's okay. n2, let me write k divides n, then k squared plus k plus 1 should divide n squared plus n plus 1, and k is positive divisor. So if n is 2, you know 1, if you replace 1 divides 2 and 2 divides 2, both of them satisfy because for 2 we don't need to check because we said necessary condition is n is 1 mod 3, so we should check for 4. For 4, you say, okay, what are the divisors? 1, 2, and 4. So 1 and 4 are obviously okay. For 4, both sides will be equal. For 1, left side 3. And we've proved if n is mod 1 mod 3, for 1 it is okay. 1 plus 1, 3. So you need to only check 2. 2 squared plus 2 plus 1. We should see that does it divide? 4 squared plus 4 plus 1. It is 16 plus 4, 20, 21. And 4 squared plus 2 plus 1, 7. So it is okay. So 4 is okay. 1 is okay. 4 is okay. And now let me tell you something. N is prime. That P is 1 mod 3 is okay. Why? Because the only divisors are 1 and P. So it is okay. So N7 is okay. Plus 3 because it is prime. The only divisor is 1 and 7 and it's okay. 10. Let's check 10. The divisors are 1, 2, 5, 10. So for 1 and 10 we know it's okay. For 2 and 5 if we write for 2 squared plus 2 plus 1 divides 100. 10 squared plus 10 plus 1 and 5 squared plus 5 plus 1. 10 squared plus 10 plus 1. It is what? 111. This is what? 7. It is what? 31. So for 7, it is 7 times 1. 41. It is not multiple of 7. Okay, so we can say what? It's wrong also here. It's, let's check 111. It's 3 times 37. It's right. Okay, so N10 doesn't work. So 13 works. You can check some other answers. So let's consider some of them. For NP, for N1 we said it is okay. For NP, P is prime. That Let me move it to right. P is prime, it's okay. Now, this idea that I'm writing was also useful in one SUMAC 2022 problems that was for Stanford summer camp. The idea that we are checking one prime, or maybe we have two primes. Maybe our primes are equal, for example, p squared, or maybe it is pq that p is not q, for example, without loss of generality is, and p and q are prime numbers. And then by checking this, we will understand what should we do. So for p squared, the remainders, the divisors of n are 1, p, and p squared. 1 and n are okay. Let's check p. P squared plus p plus 1. We should see that does it divide p4 plus p squared plus 1. Now, we want to say is it correct or not. We know p squared plus p plus 1 divides itself. So if you multiply it by p squared, it will be p4 plus p cubed plus p squared. So then we will see if we subtract, it is equivalent that p squared plus p plus 1 divides p cubed plus p squared minus p squared minus 1. And then we can say what if we consider p, okay, p cubed minus this one and p squared minus this one, they will have p minus 1. So p squared p minus 1 and p squared minus 1 is p minus 1 times p plus 1. And it will be what? P minus 1 if we factor p squared plus p plus 1. And we wanted to prove this, it is okay because it's p squared plus p plus 1, it is okay. So we understand for p squared also it's okay, but p squared mod 3 should be what? P squared mod 3 should be what? Because it was a necessary condition because of 1. So if p mod 3 can be 0, 1, or 2. So for 0 it is bad, p0 means p3. For otherwise 1 and 2, then p squared will be 1 for 1 and 2. So 1 and 2 are okay. So any prime square numbers, so the next one that is okay, n is p squared, that p is not 3. It is also okay. Now let's check npq, that p is less than q. P is less than q. So here we know, let's consider greater one. Q squared plus q plus 1 divides what? And they are greater than 1. Divides n squared plus n plus 1. We can write q squared plus q plus 1 divides n squared, q squared. Let's write this one, q squared plus q plus 1. If we subtract, we can get rid of these ones. And we can factor from n minus q. So q squared plus q plus 1 divides n squared minus q squared plus n minus q. Look, you should learn how to work with divisibility. In number theory, we have two important signs: congruency and divisibility. If you learn how to work with them, you can solve 90, 80, 90% of the problems from qualifying level up to IM. So here, if I write q squared plus q plus 1 divides n minus q times n plus q plus n minus q. And then we can factor from n minus q, so you can say q squared plus q plus 1 divides n minus q times n plus q plus 1. And we know n is what? N is pq. So if we replace, for example, n pq here, you can say, okay, p, you can factor from q. If you replace, you can say q p minus 1 and n plus q plus 1. Q squared plus q plus 1 divides this. Now we can say what? Q and this, they are co-prime numbers. We can ignore this by Euclid's lemma. Why? Because you say, suppose q squared plus q plus 1, their GCD is d. This idea is so much useful when you want to prove two things are co-prime numbers. You say d when you want to find GCD. D divides q, d divides q squared plus q plus 1. So You say, okay, d divides q, also you can say d divides q squared, so d divides this minus this, so d divides 1, so because d is GCD, d is positive, so d is 1. So because they are coprime numbers by Euclid's lemma, this is obvious lemma, it has also proof. If you had any question about the proof of this idea or other important thing about number theory, let me know through my WhatsApp. So q squared plus q plus 1 divides p minus 1 times n, and you can say n is pq plus q plus 1. Okay, and we know what? We know p and q, or we can say, let's say p was less than q, q less than n, and we can say it is greater than 1. Okay, so here we get rid of q. Now this one. We can say what? We can say it is what pq here we had. What we had n plus q plus 1. So we want to see, can we write a better thing instead of this? Okay, so for example, we can say q squared plus q plus 1 is 0 mod exactly the same number, q squared plus q plus 1. So here we have q plus 1, so you can say q plus 1 is congruent to take this to right hand side, like equality, you can use that. So you can say q plus 1 is congruent to negative q squared. So if you write it in congruency and change it again to divisibility, you can say q squared plus q plus 1 divides p minus 1. You can replace q plus 1 because it is equal mod this. pq minus q squared. So here we can factor again from q and say what? Q times p minus q, p minus 1 times, if you factor from q, it will be p minus q. And then we can say what? Let's see. Q and this we proved here. Let me show you. Here we proved these two numbers are these one coprime numbers. So you can again by Euclid's lemma, you can get rid of q and you can write this. P minus 1, p minus q. Okay, so here we know what? We know p is less than q and greater than 1. So here we can do what? We can write this part. We can change it to q minus p because the sign is not important, type by negative 1. So here we can say q minus p is greater than equal 1 and p minus 1 is greater than equal 1. So right side is a positive number, left side is a positive number. So we can say q squared plus q plus 1 is less than or equal p minus 1 times q minus p. And we can say p is at most what? P is at most q minus 1. And if we want to write this, q minus p is at most what? Q minus 1. Q minus 2 you can write. Because p is at least 2, if you want to maximize this, you should minimize p because it has negative sign. So because p is greater than or equal to q minus p is less than or equal to negative 2, so we can write this. And now here, q squared plus q plus 1 is less than or equal q squared minus 2q minus q plus 2. So we can cancel these two, and you can say negative 3q, take it to left hand side, 4q is less than or equal 1, but p is at least 2, so q is strictly greater than p, so q is at least what? Q is at least q here is at least greater than p, at least 3. So it is at least 12. So we've reached contradiction for this part. Now, here, if you pay attention, we didn't use p and q are prime numbers, and or for example, they can also be equal. P is less than q, strictly less than q. So we can say something. We proved for what numbers it is okay for 1 p squared. So suppose P and Q are not prime numbers, any numbers. If n is not prime and n is not prime squared, so for example, if n is prime cubed, you can write p times p squared. And for example, one of them pq, because we didn't use p and q are primes. You could write anything. For example, you could write n equals a times b, which is a less than b greater than 1. So if n is not p squared, you can, and not p and not 1, you can write n in terms of ab, that a is greater than 1 and b is strictly greater than 1. So we proved for other cases it's impossible. So the only answers are n1 and p, that p is a prime and p mod 3 is 1, because it was necessary condition, and is p squared and p is not 3. And for all other cases, it is not correct. Okay, you can use my other videos about Harvard, MIT, and also Olympiad problems, international level. And please subscribe my YouTube channel and turn on notification and like my video to have next videos. And if you had any question about the solution of this problem or other problems, feel free to send message to my WhatsApp number in the description or comments. Thanks for seeing my video.